My name is Kyle Hecker, and this is IQE number 7 for Fluids 307. The first question, the conceptual question, is explain the Euler turbo-machine equation and how shaft work is implemented into it. So the answer to this is, of course, to write out the Euler turbo-machine equation. And what it is T shaft is equal to rho V dot, so the volumetric flow rate, times the quantity of the radius times the velocity of 2 minus the radius times the velocity of 1. So when you do this for any sort of machine at a rate, you subtract the rate times the velocity of the second minus the 1 times the first, and then multiply it by the density and the volumetric flow rate, and that in turn will give you the shaft work. And how shaft work is implemented is shaft torque is equal to the change in momentum from inlet to outlet. Okay, and then the calculation question is sort of a fun one, as it's coming from Africa. So it asks, water is flowing down Mount Kilimanjaro and passes through a cylindrical pipe full of rocks, as shown in the figure below. It is not very well drawn to scale, but this is Mount Kilimanjaro, and this is the flow coming off, and the little dots are the rocks, and here's the pipe. And then this little black at the bottom is what we'll get to in a second, as I can tell you. The entrance is 2 meters wide. The rocks are 50 centimeters in diameter, and the pipe is 8 meters long. If the porosity of the rocks is 47%, and there's initially 1 meter of water in the bottom of the pipe, that's what these little lines down here are. At high season, at the best water melting season for Kilimanjaro, what will the flow rate of the water be off the Mount Kilimanjaro? So we have all our known values out of this word problem. We're looking for Q, or V dot, so volumetric flow rate. We're going to assume that pressure drop and kinetic energy are 0, and we're at 25 degrees Celsius. And then our properties at 25 degrees Celsius, we have viscosity and density. And then we move on to the solving part. We get rid of pressure and kinetic for both, and then we have our Z terms with our F right here. And then F turns out, when you put your numbers in, we get 9.81 times 9, which is 88.29. Then we're able to use this number to solve for a velocity, and this velocity is use this equation with epsilon and rho and the length and mu and the density or the diameter of the rocks. We plug that in, we get 14,353, and then we multiply it by the area or the diameter of the area going into the pipe, and we get a very large flow rate. So this would be a really good day for Africa, but this is how this equation would be solved.